Hey there, in this video we're going to go over section 7.2, which is confidence intervals for a single mean. Last time we talked about finding the confidence intervals, or in the previous video for section 7.1, finding confidence intervals for a population proportion. So now in section 7.2 we move on to finding the confidence interval for a population mean. So last time we did a confidence interval is found by using the statistic or the point estimate plus or minus your margin of error. So a statistic plus the multiplier times the standard deviation of our statistics. So for the section 7.1, our point estimate was our p hat, the sample proportion, plus or minus our critical value. This is the multiplier times the standard deviation of our sampling distribution. So it's the square root of p hat times q hat over n. In this section, we're going to talk about the confidence interval for a population mean. And so when we have large samples and we can assume a normal shape distribution, there are shortcuts that we can apply to find this confidence interval. So we're going to still use the statistic plus or minus a multiplier, the z-score multiplier times the error when we know the population standard deviation. So remember, sigma is the symbol for population standard deviation. And we're going to use the statistic plus or minus a t critical value from a t table that we're going to talk about times the error when we don't know the population standard deviation. So this is a pretty big deal. So when we know the standard deviation of the population, then we use the z-scores as we did for proportions. We're going to be looking at the z-scores table. But when we don't know sigma, or we have a small sample, so less than 30, we're going to use a t-distribution. Just to remind ourselves, the central limit theorem for the sample means was that if you have samples that are greater than 30 or your sample comes from a population that is already approximately normal, then the standard deviation is equal to the population standard deviation divided by the square root of n. And the means are the same. The mean of the sampling distributions is the same as the population mean. And if we don't know, so let me highlight that, when we don't know the value of the population standard deviation, then we use the approximate, the sample standard deviation as divided by the square root of n. So let's try this example of sleepless nights. And this is an example when the population standard deviation, so sigma, is not known. So my question is, how much do ARC students sleep on a typical night? And let's make it more specific and ask about the previous night. So I assigned a survey and asked you to take it, and so that was about the prior night. Is the average less than the recommended 8 hours? So it is recommended that people sleep 8 hours in a night, so I wanted to see how much do ARC students sleep on a typical night. So what is the, describe in words the relevant parameter of interest in the study, and what symbol would you use? And so looking back at the example, notice that it says, is the average less than the recommended 8 hours? So we are looking at the average. So that is going to be our parameter. So what symbol do we use for average? So we're going to say that the parameter is the average number of hours slept on a typical night. And because we're dealing with a population parameter, our symbol is going to be the Greek letter mu. So mu is the average number of hours slept on a typical night, and we can be a little more specific and say by ARC students. So that is our parameter. So let's investigate whether the mean amount of sleep last night for the population of all students at American River College, your school, was less than 8 hours. So this is going to come in handy for our hypotheses. So we want to investigate whether ARC students sleep on average less than 8 hours. And we're going to assume that the population is normally distributed. So this is mainly here so that we can use the central limit theorem later. depending on the size of our sample. Because if our sample is smaller than 30, we may not be able to use the central limit theorem. So this says, well, assume our population is normally distributed. So it's guaranteeing that we can use the central limit theorem. Now, express the null and alternative hypotheses for investigating this question. Use words and symbols. So we want to investigate whether the mean amount of sleep is less than 8 hours. So the null hypothesis is usually the standard, right? The claim. So the standard is the recommendation is that people sleep on average 8 hours. So that's going to be our null hypothesis. So in words, we can say the average number of hours slept on a typical night is 8 hours. And then in symbols, we can say the parameter mu is equal to 8. And the alternative hypothesis is usually the question, what are we looking at? What do we want to investigate, right? The conjecture. So we want to investigate whether the mean amount of sleep, let me highlight that real quick, is less than 8 hours. So that's what we want to investigate. So that's going to be our alternative hypothesis. So in words, we can say the average number of hours slept on a typical night is less than 8 hours. And in symbols, we're going to say H sub A, right, for alternative. The 0 is H null, or the null hypothesis, and HA is the alternative hypothesis. So the average, the mean number of hours slept the previous night is less than 8. So ideally, how would you obtain a sample from the population of all students at your school? So what will be the ideal situation? Ideally, for any study, we want to make sure that we have a simple random sample. So that will be the ideal. We want to obtain a simple random sample. And so we will say go to random places at the college, right, to survey students from the population. So the student union, the sporting event, or tutoring center, random ARC classes, not even necessarily classes that you're taking, but just you want to get a really random sample of all ARC students. So you would go to places that are not necessarily convenient to you. What variable would you measure on each student? We will measure the number of hours that they slept last night. So while obtaining a simple random sample of students from ARC is an ideal way to attempt to get a representative sample, there is no question that it will take a lot of time, effort, and energy for you to make that happen. Sometimes we have no choice but to rely on a convenient sample instead. Right? Look above at part D. So to get a simple random sample, some of the ways that I listed is go to random places at the college to survey students, the student union, sporting event. So in order for you to go to all those places, go to a sporting event, go to a tutoring center, maybe like find the times that the tutoring center is the busiest, go to random ARC classes. So that takes a lot of time, effort, planning. And so some people may not be up for the challenge. And so a convenient sample is used instead. So like me, in this case, I'm going to use this class as our convenient sample. So that's why you guys filled out the survey. How many hours did you sleep last night? So that was a very convenient sample for me, even though it is still, you are ARC students, so it is a sample of ARC students, but it's a very convenient sample, right? So we will revisit the implications of using this class as a sample of ARC students later when we evaluate our study. For now, let's gather the data. So you already took the sleep survey, and I have uploaded the data to StatCrunch. So if you want to pause the video and you can go to StatCrunch and take a look at the data. But I'm gonna move on to part G. Identify at least one way that your class is likely a good representation of all students at ARC in terms of hours slept last night. Well, and I already mentioned one of the reasons that you are a nice convenient sample is, well, you are ARC students. So you are part of the population. So that one works. Any other reasons? I'll look forward to seeing your notes and see what other reasons you put in there. And I'll try to then put some of those reasons back in this notes. Identify at least one way that your class is likely not a good representation of all students at your school in terms of hours slept last night. So what is at least one way that this class is not a good representation of all ARC students? So pause the video, kind of think about it, and then make sure you add that in your notes for submission at the end of the week. Some of the things that come to mind is that this is an online class instead of an in-person class, right? Like if someone's taking a STATS 300 class in person at say 9 a.m., that may affect what their hours of sleep the previous night. What else? Maybe the reason you're taking this class online is because you work full time. So varying schedules. And so if you work full time and then you're taking this class, that may affect the hours of sleep that you get at night. And so there could be various things, right? This isn't a representative of all ARC students. So there are some drawbacks to having a convenient sample like this. All right, so let's use the data from your class in StatCrunch to find the following summary statistics. So go on to StatCrunch and let's find the sample size, sample mean, and the sample standard deviation.
So once you are in StatCrunch, make sure you are logged in, and let's go to My Groups and then find our group and access the data. And so we're looking for sleep survey results, and so here we go. So sleep survey, and so here's our data. So we want to find our mean and standard deviation. So let's go to Stat, Summary Stats, and then Columns. And you can kind of, by looking at the data, let me go back a little bit. Can you tell what the mean might be? So you guys are not sleeping very much. So we have a 3 hours of sleep, 4 hours, 5 hours, and then what's the most? 8.5 hours. So, but by just looking at the data, it's hard to see the mean. So let's go to our summary stats, and we want to do columns, select sleep survey. We want to know, even though we can see here n is 24, let's just select n. We want also the mean, so control, and then keep holding control down, and standard deviation. So then what's over here on this white box is what we're going to find. So the sample size, the mean, and the standard deviation, and then click compute, and it gives us our data. So the mean is 6.414 and the standard deviation is 1.48. So the mean number of hours that you guys slept the night before taking the survey was 6.4 hours, and with a standard deviation of 1.48 hours. So this tells us that the information that we need. Now, can you spot any outliers? At first glance, right, you might think like, oh, 3 might be an outlier, but then there are 4s, there are a few 4s, 4.5. So is 3 really an outlier? So how can you find the outliers? So we can practice. How do we do that? We can look at a box plot. So select box plot, sleep survey. And with box plots, it's really, really important to draw the boxes horizontally, right? We want the horizontal axis to be the hours slept. If you don't do that, then things are going to be on the y-axis, which is not what we want. And I'm going to mark the mean just to see, to help me gauge whether it's skewed right, skewed left, or normally distributed. So let's compute. And so here is our box plot, and it does not appear that we have outliers, right? How can we tell outliers in a box plot? Usually they show up as dots beyond the fences. So here's our mean, 6.41. Now remember the bar in the middle there, that's the median. So if you hover over it, it tells you, right, the median 6.625, and we have our quartiles, our lower limit 3, which is not an outlier. If I wanted to see what an outlier looks like, just to remind you, I can say somebody here slept 16 hours. Hopefully not. That may not be all that healthy, but sometimes you need it. So now let me go back to my box plot, edit, and I just want to capture that 16, so everything will be the same. Draw boxes horizontally and then compute. And now notice that now it shows 3 as an outlier, and that's just because the 16 pushed everything over, right? The mean increased, the median increased, and so now notice that it gives me 16 as an outlier and it gives me 3 as an outlier. And so now you can see how that changed it. So now the median and the mean are very close to each other, right? The mean is 6.798. The median, what was the median? 6.75. So very close. So let's go back and get rid of that 16. And this is something you can do just to see, like, are you doing it right? You know, like, should that be an outlier? You can throw in another outlier just to make sure. So edit, and then everything is the same. Compute. So there's my actual box plot for our actual data with no outliers. All right, so let's copy this into, oh, by the way, is it which way? Skewed left, skewed right, normally distributed. The mean is to the left of the median, so this is going to be left skewed, and you can tell also that it has a longer left whisker, so this is going to have a left tail. You could also, sometimes the dot plots are better to see that, so you could do a dot plot. And so we can see here, right? There's the dot plot, and you can see that it has a left tail. Sometimes I like to scrunch it up so I can see a little bit better. If it's spread out, yeah, you can still kind of see the tail, but you can resize it to see, like, oh, most of the data is on the right. It has a left tail, so that means it's skewed left. So good practice with these guys. But what we want is our n, the mean, and the standard deviation. So let's copy those and go back to our notes. And we'll get 1.483. So now, based on your sample data, what is your best guess or estimate for the value of mu? That is the average number of hours of sleep that ARC students got the previous night. Explain how you could check to see if your estimated value is indeed a plausible value for mu. Well, based on our data up here, so 6.4, we do have a fairly large sample, 24. So definitely we can say is less than, mu appears to be less than 8, which is the, well, our hypothesis is that the mean is 8. So I will probably guess around 6.5, but you know, we're not entirely sure. So I'll just put double question mark there. So, but the key idea here is that a confidence interval for the population mean with sigma not known. So let me highlight that. Either or both of these conditions are satisfied, right? With using the central limit theorem now, the population is normally distributed or n is greater than 30. If n is less than 30, automatically use the t distribution. Here our n is less than 30, so we'll use the t distribution. And the sample is a simple random sample. I do have a slight convenience sample, but technically you guys are a sample of ARC students, so I can say it's a simple random sample. So in order to find the confidence interval, we need the margin of error, which is E equals to T alpha over 2, so this is our critical value, times the standard deviation given to us by the central limit theorem. So S over root n, right? So going back to where using the central limit theorem, right, when we don't know sigma, well, first of all, we have to come from our sample has to come from a population that is approximately normal or bell-shaped, which we were told that it is. The population of ARC students is approximately normal. And so we're going to use the standard deviation because we don't know sigma. we're going to use S over root n for the standard error. And so going back over here, that's what we're using with degrees of freedom n minus 1. Now what the n minus 1 really means is that because we're taking samples, varying samples from a population, we adjust our degrees of freedom. So essentially it's kind of almost like throwing one element out, one data value. So with a sample of 24, we will say, okay, we can differ, throw one out just in case, just to account for variation from sample to sample. So we will consider 23. You always kind of, with statistics, you always want to underestimate rather than overestimate your sample sizes. And then our confidence interval then is for the population mean, right? For mu will be x bar plus or minus the standard error, the margin of error, which is up here. So x bar plus the margin of error will give us the upper limit, and x bar minus, or sample statistic, minus the margin of error will give us the lower limit for our confidence interval. Some comments here, the student t-distribution. So if a population has a normal distribution, then we can use t is equal to this formula. And notice that it looks very similar to our z-score, right? It's the sample statistics, or sample mean, minus the population parameter. So mu, the population mean, divided by our standard deviation. And here we're adjusting for using the central limit theorem. And this is what's called the student t-distribution. We just call it the t-distribution. And then lastly, x bar is the point estimate, the observed sample mean to estimate our population mean. So x bar is for the sample, mu is for the population. So does our sample meet the requirements to approximate the population mean? Yes, our sample comes from a population that is normally distributed, right? ARC students is our population. And we will use t alpha over 2 because we don't know sigma. We don't know the population standard deviation, but also our sample is less than 30. So as it says here, when you have samples that are less than 30, you automatically use the t-distribution. And so let's calculate the standard deviation for the sampling error. So we're going to be s over the square root of n. So our s was 1.483. Looking back over here from our StatCrunch data, s is 1.483 and n is 24. So that's what I'm putting in the formula here. So 1.483 divided by the square root of 24 is 0.3027. So now let's determine a 95% confidence interval for the population mean. So these are the steps in finding a confidence interval. So in our case, it's going to be a 95%, but first is we need to find the required critical value from our t-table, and I'll show you how to do that from your textbook. Calculate the standard error. The standard error, the formula is given over here. E equals t alpha over 2 times s over root n with degrees of freedom n minus 1, and then create the 95% confidence interval by adding and subtracting the margin of error to your sample statistic, right? So you're going to do this x bar plus or minus e, and then we're going to interpret our confidence interval. All right, so let's go do that. I'm going to bring you to my notebook. So first we want to find our required critical value. So we have a 95% confidence interval. So 95% confidence, what does that mean? We want to find our alpha, right? So that means that alpha is going to be 1 minus 0.95. How did I get 0.95? 95% is 0.95 as a decimal, right? So that means alpha is 0.05. Now we want alpha over 2. And then, so that this will be 0.05 divided by 2, which is 0.025. So then this is our alpha over 2. So our t sub alpha over 2. Now we need to go and look that up on the table. So look up on t-table, the t-distribution. Now why are we doing the alpha over 2? So when we look at this comes from, we're assuming, right, normal distribution, bell shape. So when you have 95% confidence, so that means you're looking at 95% of the data is here. So then what's left on the tails? On the tails, we're going to have the remaining. So what will make it 100? 5%, right? So then this is 5% or 0.05. So when you have a two-tailed test, and we'll talk a little bit more later in the semester as what it means to be two-tailed test, so then we will do this. And for when we're looking at just one tail, so if I'm just looking at one tail, then this will be, right, this is my alpha over here. Alpha is 0.05. That's together, so then one tail will be alpha over 2. So that means that this area on this tail is 0.025. So that's kind of what we are doing when we're trying to find our critical value for just one tail. So let's go look up at our table to find the T alpha over 2. So we're going to go to our textbook and go to eText on your MyLab menu, and then click on the eText to open the textbook, and then it should load. Once it's loaded, we want to go to the table of contents, and you're going to scroll all the way to the bottom, and you're going to look at where it says z-score and t-values. So you're going to click on that, and it's going to bring up the tables. So there's the negative z-scores, then the positive z-scores, and then you're going to get our t distribution. This is the student t distribution for critical values. So we're looking at area in one tail, so 0.025. But notice that even if you did area in two tails, then it's the equivalent of 0.05. So they are the same. So our degrees of freedom were, what's our sample size? Our sample size was 24. So degrees of freedom, one less. So we're going to look at 23. So you look at 23, and where was the 0.025? One tail or two tails, 0.05. So this one, the one in the middle. So let me go back to 23, and so it's 2.069. So can you see that? So 2.069, that's our critical value. So let's go back to our notes. So back in our notes, we just found the t, so alpha over 2, or critical value, is 2.069. And so now we can do our calculation. So calculate the standard error. Now our standard error, the formula is E equal to t sub alpha over 2, or value that we just found, times s over root n. And so we can put that in here. So it's going to be 2.069. Sorry, my handwriting is awful on the tablet. And so that's our critical value that we just found, times our s over root n. So s is 1.483 and n is 24. So 1.483 over the square root of 24. So put that in your calculator and see what we get. I got 0.626. So hopefully you got something similar, rounding to 3 decimal places. Now remember, we had found this earlier in the notes, 1.483 divided by the square root of 24, which we had found it to be 0.3027. So you can just reuse that instead of having to reinvent the wheel. And so that's how I got the 0.626. If you did it exact, then your number may be a little bit different than mine. All right, so that's our standard error. Now we're ready to construct our confidence interval. So how do we do that? We do the sample statistic plus or minus the margin of error, which we just found over here, right? This is our E. So let's go back over here. So that means our 95% confidence interval is going to be the lower limit x bar, our sample statistic minus the margin of error, and then the mean is going to be in the middle, right? So we're approximating the population mean, x bar plus the margin of error. So this is the lower limit, and this is our upper limit for the confidence interval. And this is what we're trying to approximate, right? The population parameter. Remember, when it's something about the population is called a parameter. When it's something about a sample, it's called a statistic. So x bar here is our statistic. All right, so now we can say, well, x bar, what was our mean? Our mean, I wrote it up here so that I would remember, 6.415. So that's our x bar. So 6.415 minus the standard error, which is 0.626, is going to be less than the population mean, and then that's going to be then the population mean is less than our mean, 6.415, or sample mean, sample statistic, plus the standard error, 0.626. So I got 5.789 for the lower limit, and then for the upper limit I got 7.041. So that is then my confidence interval for the mean, a 95% confidence interval. So this means that the population parameter, so the mean, the average hours slept by all ARC students, we think based on our sample, is between 5.789 hours and 7.041 hours. So that is our confidence interval. So you can write it like this, or you can also write it in the interval form, which will be 5.789 parentheses comma 7.041. So this will be in interval notation, right? But then you can also say the population parameter mu is between the lower limit and the upper limit, which is already kind of interpreting the confidence interval. So we are 95% confident that the average number of hours slept by ARC students is between 5.789 hours and 7.041 hours. So that's one of the things we can say then in interpreting our confidence interval. So I'll let you write that in your own words, but essentially you want to say, right, I am 95% confident that the population parameter, so the average number of hours slept by ARC students, is between, and then the lower limit and the upper limit. Now back to our main notes. So unlike the z-score multipliers used for the confidence intervals when we had population proportions, there are a lot of t-score multipliers used for the confidence intervals for quantitative data, right? Population mean. The t-score multipliers are based on the sample size and account for the variability between samples. So as you take samples from the same population, right, samples of the same size from the same population, we adjust by one data value. So that's why our degrees of freedom are n-1. And so if we increase the level of confidence, say to 99%, you need a new t-score multiplier. So let me see if I still have them up. So yeah, notice that now here we have our t multipliers based on the sample size. So if I'm looking at 95% confidence interval, then my alpha is 0.05, right? Alpha of 2 will be 0.025. I think is off the screen here. But notice how the t multipliers change, the critical values change. They're getting smaller and smaller. As your sample gets bigger, the multipliers are getting smaller. And in fact, notice that when you have really large samples, so the last one, notice that this is actually 1.96, should look familiar. This is the z-score for a 95% confidence interval, right? So what this means is that as the samples get larger and larger and larger, this distribution curve becomes flatter and flatter and flatter. Not flatter and flatter, but it becomes more like the normal distribution, more bell shaped. So as you go really high sample size, then you're essentially looking at a z-score multiplier. But right, as you, if I take a sample of, you guys were 24, if I had a bigger class of say 38 or 39, then my multiplier changes. So that's what I mean by the t-scores change. So this is really important to have your t-distribution table. All right, oh, there it is. Now you can see the area in one tail. All right, so if I wanted to find a 99% confidence or t multiplier, then 99% will be what? So I will have to do 1 minus 99, right? So my 0.99, so that will put me at 0.01, which is in two tails is right here. So in one tail, this 0.01 over 2. But either way, I'm looking at the first column. So for our sample of size 24, adjusting for variability, degrees of freedom will be 23, right? 24 minus 1. So my new t multiplier will be 2.807. And so now we could go back and find a 99% confidence interval for our sample. So go ahead and do that on your own. Find a 99% confidence interval. And what if you decrease your level of confidence? And so what I want you to do at the end of that is look at the confidence interval that we found together, 95% versus the 99% and versus the 90% confidence interval. What is happening as you increase the level of confidence? So look at the 90. Once you complete 99 and 90, look at the 90% confidence interval. Then look at the 95. Then look at the 99, right? So what is happening to your confidence interval in terms of its width? So think about that. I'll record another video to do the last example.